Okay, you guys, so for 4.2, we're going to go over the mean value theorem or the MVT. Excuse me. But in order to get there, we got to kind of talk about a few things first. One of the first things we have to talk about is Rolle's theorem. Now, Rolle's theorem says let f of x be a function that satisfies the following three conditions. So these three things have to be true in order for you to work with Rolle's theorem. Okay, so first of all, Rolle's theorem says you have to know that f of x is a continuous function on a closed interval, a to b. You have to know f of x is differentiable on a closed interval, a to b. And the third thing is you have to know that f of a equals f of b, which basically just says that when you plug the two endpoints in, you end up at the same height. So then there exists a number c, an element of ab, such that f prime of c equals to 0. So this very end part right here is what we're really concerned with. This is kind of the big deal of Rolle's theorem. Now think about what that's saying. That's saying that f prime of c equals 0. So remember, f prime stands for the derivative, which is the slope of the tangent line, and they're telling you that the slope of the tangent line is equal to 0 at this location c. So basically, they're telling you, or they're promising you, that at some point you're going to have a tangent line or a horizontal tangent line on your graph. Now let's think about why this is happening. So this isn't really a proof. This is just kind of a motivation to our thinking, okay? So suppose we're right here. So suppose we're looking at this graph right here. So in this graph, we have a continuous function, okay? The function is continuous and it is differentiable everywhere because there's no sharp peaks or valleys where the derivative, the rates of, I'm sorry, it's not the rates of change. The slopes of the derivative approach different values at any given location. These are all like a nice smooth curve. So this is differentiable everywhere. And then we see that right here at this value, it has a height of whatever that is at f of a. So this is f of a. Maybe I should write in a different color. Let me do this. F of a equals f of b, right? Because they both have the same height at that location, okay? So here and here we have the same height. So that's step one, check, step two, check, step three, check. We have satisfied the three criteria for Rolle's theorem to give us its promise. So here's the promise of Rolle's theorem. It says if it's continuous, and if the function is continuous and differentiable and the endpoints reach the same height, then you know without a doubt there is some c in that interval a to b, in between a and b, such that f prime of c will equal 0. Well, let's look right here. Look right here. This value right there, that is a horizontal tangent, and guess what that value is? That's c. Okay, now we come over here, same thing. We see right here, we have a horizontal tangent here. Oops, I think I erased the a right here. So this would be f of a equals f of b, whatever that height is, we don't know. And this would be our c right here. So that's all Rolle's theorem is promising. You give Rolle's theorem those three things, and Rolle's theorem promises you there will be a point, c, where you'll have a horizontal tangent line, or the slope is equal to 0. Now, what this really means for us is at some point, it's either going to change direction or change concavity or something like that. We know something happens at that C where the horizontal tangent will be 0, okay? So that's Rolle's theorem's promise, okay? So let's kind of look at what it does. So it says find all C that satisfy Rolle's theorem for f of x equals 4x squared minus 20x, sorry about that, plus 29 on the interval 1 to 4, or explain why no such C, or explain why such a C is D and E does not exist. So the first thing you have to do for all of these problems is you would have to verify that you've satisfied the hypothesis. So first thing, is it continuous? So f of x is continuous. Why? Why is f of x continuous? Well, you guys know this. It's continuous because it's a polynomial. Because f of x is a polynomial. And you guys all know that polynomials are always continuous. They're nice and smooth. That also leads us to part 2. F of x is differentiable And remember, all differentiable means is that you can differentiate it. Okay, it's differentiable since f of x is a polynomial. Remember, all polynomials are smooth. They don't have any sharp edges, no weird like absolute value looking graphs. Everything is nice on a polynomial. I guess I'll write it out since I wrote the other one all the way out. And then step 3, f of a, so let's do f of 1 would equal 4 times 1 squared minus 20 times 1 plus 29. That would equal what? What do we get from that? Let me see, that's 4, 9, what do we get, 13? So I think we get 13 on this one. And let's see what we get from f of 4. So this would be what, 4 squared, so that'd be 64. Well, 4 squared times 4 is actually 4 cubed, minus 80 plus 29. So that would be what, 80, 93 minus 80 would be positive 13. So then this means that f of 1 equals f of 4, right? So check, check, check. So we have the 3 hypotheses, or the 3 parts of the hypothesis to the Rolle's theorem. Now, the follow-up, or the requirements for Rolle's theorem, the follow-up then says that we are now guaranteed that there will be some c in between 1 and 4 that we will get the derivative equal to 0. This is a promise that Rolle's theorem has made to us. So now we need to find f prime of x. So we take the derivative of this, that's f of x. So we get 8x minus 20. We set this equal to 0 and we solve. 8x minus 20. So 8x equals 20, divide both sides by 8. So then x equals, we can cancel a little bit, divide by 4, we get 5 and 2, so we get 5 over 2. Now here's the thing, 5 over 2 is 2.5, which is in between 1, 4, which we knew would happen. How did I know for sure I was going to find something? How did I know for sure that I was going to get an answer? Okay, well, I knew for sure because Rolle's theorem promised me if you satisfy the 3 criteria, part 1, part 2, and part 3, differentiable, continuous, and the f of a equals f of b, then I promise there will be an f of c. So the last little bit is, maybe I should actually rewrite this real quick. Normally what they want you to do, I've seen it in the homework, is they then say, well, then f prime of c has to equal 0, which is 8c minus 20. So they substitute in a c. So then we have 8c is equal to 20. So then we have c is equal to 5 halves. That's what I did last time. And this would be our c that satisfies, or that is the conclusion of Rolle's theorem. Okay, and it's really, it's an x because it's on the x-axis, but they're just, that's how the theorem's written. So we're going to answer it with the c. Okay. So keep in mind, what if it was discontinuous? Well, if it was discontinuous, then I could take a drawing and I could do this, and I could do this graph right here. Oops. I could do this graph. Let me make a more blatant one. I could make this graph, put a thing there, put an endpoint there, put an endpoint there, and I guess I could do this. That wouldn't be a function. Let me do this. We want to do this better. So here's a situation. Here's my A, here's my B, and f of A equals f of B. So I get the same height, which is a good thing. However, right here, there's a discontinuity. So because there's a discontinuity right there, that's where my derivative was supposed to equal 0, but it's not there. So you'd say, oh, Rolle's theorem's broken. Well, it's not that Rolle's theorem lied to us. Rolle said it doesn't promise anything. It will not give you the conclusion of Rolle's theorem, which is this part. This is the conclusion of Rolle's theorem. You aren't allowed to get this. You aren't promised this unless the top 3 things have been satisfied, okay? So that's the big deal with Rolle's theorem. You have to fulfill its 3 requirements, but then once you do, then it promises you will find such a C, okay? All right, so now let's look at another one. Now this is a problem similar to this is in your homework, but this is a little bit harder idea. So normally, if we had an in-class exam, this would be almost guaranteed to be on your exam, but we'll see how it goes with the online, or if we have an online exam. So it says, prove that 1 plus 2x plus x cubed plus 4x to the 5th equals 0, 1 and only one real root. Okay, so we would like to try to use Rolle's theorem since we just learned it. There's other ways you could kind of talk about this, but I want you guys to kind of see the power of Rolle's theorem. And in higher levels of math, sometimes you can't directly prove things. Sometimes it doesn't work quite how you want. So you have to hit it from the side. You have to attack the problem from the side. So what we're going to kind of do is we're going to attack this problem from the side. We're going to use proof by contradiction. Okay. So this proof is going to come in two parts. Okay. So the first part is we have to prove existence. So you guys notice that there's two things you have to take into consideration. You have to first prove that it has one root. Then you have to prove that it has only one root. So this is like two parts. You have to prove both of these things. So let's first prove existence of a root, okay? Now there was something that we learned in pre-calc or in other algebra classes called the intermediate value theorem, okay? So what the intermediate value theorem promised, well, what we used it for a lot was we used it to verify that roots exist, okay? That it crosses the x-axis at a certain point, okay? So we need to show existence of a root, okay? So first what we're going to use is the first thing we're going to do is we're going to use the intermediate value theorem, okay? And we're going to use the IVT on the interval 0 to -1. Now you might say, well, how did I come up with this? Well, you could take out your calculator and you could kind of estimate where you think there's a 0. So we graph this function on our calculator, 1 plus 2x plus x cubed plus 4x to the 5th, okay? And then it looks like somewhere in between -1 and 0, it crosses the x-axis. So that sounds like a good starting point. So I'm going to choose between, oops, I wrote this backwards. Sorry, I don't know why I did that. It's -1 to 0. Sorry about that. So we're going to start with that. And it's just kind of our best guess. We think that's a good interval to check. We're pretty sure, well, we can tell from the picture that it definitely crosses the x-axis, but we want to prove it with more than just a picture. So we know that f of x equals 4x to the 5th plus x cubed plus 2x plus 1 is continuous. Remember, the intermediate value theorem needed continuity. Okay. So we know it's continuous. Why? Since remember, we love polynomials in calculus because we can just, there's so many facts that we know about them that we can just kind of say, oh, this is a polynomial, boom, we have this, boom, we have this. Those of you that go on to take linear algebra, something similar will happen when you talk about determinants or inverse functions. There'll be all these relationships between inverse functions, determinants, and the moment that you say the determinant of a function is 0, you have all of these things that follow. The moment you say the determinant of a function is not 0, you'll have all these things to follow. So there's sometimes these kind of cool things that once you know that fact in math, it unlocks all these other ones. And polynomials are one of those things. You know it's continuous, you know it's differentiable, you know you can integrate it. There's all kinds of things that you can do with polynomials. Okay, so we know that f of x is continuous since it's a polynomial. And another fact is we know that f of 1, I'm sorry, -1, if we plug -1 in, I believe, let's see, -1, we should get -6. And if we plug we plug in f of 0, that's the easy one. That's going to be 1. So we know that we're getting two different values, okay? We're getting a positive value and we're getting a negative value. Now, what did you have to cross in order to get from a height of -6 to a height of +1? Right now, just think about it graphically. You don't have to write this as part of your proof. But if you have a graph and you are here at -1 and you have a height of -6 down here somewhere, and then at 0, you have a height of 1 right here, and you're continuous, I don't care how many curves you do, at some point, you had to go through the x-axis. So what's your height at this moment right there? Your height is 0, correct? So we know that there has to be a root, because a root means, remember, that it's equal to 0. It zeroes out the function. So we know that since -6 is less than 0 and 0 is less than 1, normally the intermediate value theorem promises you there's some n that's in between these that is guaranteed. Well, the one that we're looking for is 0, so we're going to go with that. So we know that there exists a c in -1 to 0 such that f of c equals 0. And what does it mean for there to be an f of c equal to 0? It means there's a root. So we have shown that, because, and the kind of the non-super fancy way to say it is, you notice that we changed signs. We went from a height of -6 to a height of +1. Whenever the signs alternate in the intermediate value theorem, it's a guarantee that you had to cross the x-axis, which means you had an x-intercept, which means you had a root. Okay, so if we know that it crossed the x-axis, we know it had a root, therefore we know that f of c had to equal 0, right? We knew this. We knew this fact, okay? So we have just shown that there had to be at least one root. Now, what we have not shown is that there's not more than one. Maybe there's 2, maybe there's 3, maybe there's 4. Remember, the intermediate value theorem doesn't tell us how many, and it doesn't even tell us the number, like what the actual c is. It just promises us that there is one. It just doesn't tell us how many. So now step 2 is we need to prove not more than one real root. Okay? So we need to show that, we need to show not more than one root. I guess that's, you could write that a little bit with better English, but let's just go with it. So what we're going to do is assume 2 roots then, 2 real roots, okay? Let's call it R1 and R2. And let's just say that R1 and R2, whatever they are, they stand for roots to the function, because now here's the thing, here's one of the coolest parts of math, okay? It's proof by contradiction. So what you do is you're saying, you know what, it's hard for me to prove that there's not more than one. And, you know, if somebody's trying to argue with you, they're going to say, hey, there's more than one. You know, I don't believe you that there's only one. I think there's more than one. In case you tell them, okay, fine. Or you tell her, okay, fine. Let's say there is more than one. Let's say 2, for example. So we're going to assume that somebody arguing with us is right. We're going to assume that somebody else is right. So we're going to say, okay, there is 2 roots then, or more. We'll just do 2 arbitrarily, but you could have done 3 or 4, whatever. So we'll assume there is 2, okay, or more than 1. Okay, now we're going to be using the interval R1 to R2. Those are going to be our 2 roots, okay, and we're going to say f of x, let's see here, how can I say this? You know, let me write this in a better statement. Let's look at the interval R1 to R2. These are our 2 roots, okay? And let's say that f of x is continuous on this interval on, oops, wrong letter, 1, R2. How can we assume that? How do we know that it's continuous on R1 and R2, and we can even say it's differentiable. How do we know? Since f of x is, because f of x is a polynomial, it's continuous and differentiable on all real numbers. So it's definitely continuous and differentiable on R1 to R2. Now here's the thing, what's the final criteria for Rolle's theorem? Because remember, Rolle's theorem is going to promise us something. So we're going to say, we're looking at this interval R1 to R2, okay? Rolle's theorem says, give me these three things and I will promise you that f prime of c is equal to 0. There will be some c in there. Well, if they're both roots, right? If they're both roots, R1 and R2, that means when you plug them into f of x, what should your answer be? Your answer should be 0. Your result, your value that you put it should be 0. So we know that f of R1 equals 0, but then we also know that f of R2 has to equal 0. And again, if you're not sure why, just think about what it means to be a root, what it means to be a 0 of a function. Okay, so we know this is true. Now, if you think about what we just did, we just found on some closed interval, R1 to R2, we know that f of x is continuous, we know that f of x is differentiable, and we know that f of R1 equals to f of R2. This is step 1, or part 1, part 2, and part 3. We just checked off the 3 criteria for Rolle's theorem. So according to Rolle's theorem, then we now have a money back guarantee. Then we know that there must be some f prime of c, there must be some c in between R1 and R2, where there will be another root. So f prime of c has to equal 0. So what I'm going to do is I'm going to find f prime of x. This is what we were promised. We're promised this truth. F prime of x is equal to, let's take the derivative, that would be what? 20x to the 4th plus 3x squared plus 2, okay? And then we know that this is f prime of c equals 0 equals 20c to the 4th plus 3c squared plus 2. Okay, now do you notice a problem here? So you could try to solve this. Let's try to solve this equation right here, okay? So take a minute, see what you get. See if you can solve for c. Because remember, Rolle's theorem promised us it has to be there. Okay, Rolle's theorem promised it has to be there because it's continuous, it's differentiable, and you know that f of R1 is equal to f of R2. Okay, so hopefully you've paused the video and tried it. But here's the problem, is when you take something to the 4th power, what type of answer are you going to get, positive or negative? You're going to get a positive. Plus 3 times c squared. When you square something, what are you going to get? A positive. And then when you add 2 to it, you're going to get a positive. So a positive plus a positive, oops. So a positive plus a positive plus a positive plus 2. Well, that's going to be some positive. How are we ever going to get back to 0? We're never going to be able to get back to 0, right? So because of this, we get to say something. F prime of c can never equal 0. Well, why is that bad? Now think about that for a second. We were promised this would happen, and we just did all this math, and we found out that this actually cannot happen. Well, that's a huge problem, because either that means Rolle's theorem has been wrong all along, or possibly our assumption of 2 roots was wrong. So either our assumption's wrong or Rolle's theorem's wrong. Well, this is called a proof by contradiction, because Rolle's theorem has been proven to be true always, okay? So that means that our assumption of 2 roots must be wrong. Well, then what must be true? If 2 roots don't exist, then it must only be 1. So we have now shown that there is 1 root right here, with part 1. And we have shown that there's no more than 1 real root with part 2. So we say, since the derivative cannot, or the derivative will always be positive. It cannot equal 0. Therefore, we have a contradiction. Okay? So, what we assumed must be wrong. Because we're finding a contradiction with Rolle's theorem. Okay, so if there can't be, so what we assumed must be incorrect. No two real roots. Okay. What we assumed, fix this. Okay, so therefore we have a contradiction. What we assumed of two roots is incorrect. Okay, there must only be one real root. Okay, now we did it in two parts. We proved there is at least one real root with the existence using the intermediate value theorem, and then we use Rolle's theorem to prove there is not more than one real root. Okay, so that is a little proof like that. Normally people have a really hard time with that problem. Okay, so now let me write down the MVT, the mean value. So the mean value theorem says let f of x be a function that following criteria. One, f of x is continuous on a closed interval from a to b. 2, f of x is differentiable. On a closed interval. On open interval. Be differentiable on the intervals. So we get to then say, then there exists a number C, an element of AB, such that f prime of C is equal to f of B minus f of A all over B minus A. Okay, so f prime of C is equal to f of B minus f of A. Okay, now think about what this is saying. Okay, so it kind of sounds an awful lot like the mean, or a lot like Rolle's theorem, but it's not exactly Rolle's theorem. I guess you could say Rolle's theorem is a specific case of the mean value theorem if you wanted to say that. It's a specialized version of it. But notice there's only two criteria, that is continuous and differentiable. So anything that's a polynomial, the mean value theorem, you can already talk about it like this. It says if you give me the fact that it's a continuous function and you give me that it's differentiable on an open interval, then I know there must exist some C in AB such that f prime of C is equal to f of B minus f of A all over B minus A. But now remember, what is f prime of C? This is the slope of the tangent line. And then this is the slope of the secant line. Now think about what this is. Now here's the thing. Let's suppose that you're driving to Los Angeles. Let's say you're going to LA, okay? And you want to talk about your instantaneous rate of change, which is your derivative. And then your secant line is your average rate of change. Remember that. This is your, average rate. And this is your instantaneous rate of change, right? So here's one way to think about it. One way it was explained to me when I was younger is, suppose you're driving to LA, okay? And I tell you that you drove from here to LA and your average speed was 75 miles per hour. On average, your speed was 70 miles per hour. So your average rate of change was 75. What that means is, now think about it. At some point, if you average 75 miles per hour, did you have to have a point where your instantaneous rate of change was also 75 miles per hour? Now think about it. Let's just say that you started measuring from 60 miles per hour, and then you stopped measuring at 87 miles per hour, and you averaged it out over whatever the time frame was, and your average rate of change was 75 miles per hour. Well, at some point, in order to average 75, you had to go through an instant where you were going 75 miles per hour exactly, instantaneously. So what the mean value theorem is basically saying, if you think about it graphically, is it's saying that there is a point on a graph that if a function is continuous and differentiable, that there is a point in that interval where the instantaneous rate of change and the average rate of change must be the same number. Okay, so that's all it's saying. All right, so that's the idea behind it. And you could do a drawing. Oops. You could do a drawing like this. And let me do my best to try to draw. Oh, let me do my best to try to draw something decent for you guys. Okay. So let's say that this is our interval A, and let's say that this is B over here. Okay. And this is f of A, and this is. So what this is saying is we could draw a tangent line. We could draw a secant line in green from here to here. Okay. So we could have this line. Okay. And there is also locations that would have that same slope right there and right there. This would be our C, and this, oops, you guys get the idea. And then this would be our D. So in this case, there were two locations, but it's only guaranteeing that there's at least one C. There might be more, but there is a number C that would make this happen. In this case, it was a C and a D. So that's what it looks like graphically. And then here's kind of what it is in words. Okay. Now we're going to use all of this information to try to prove the mean value theorem. Okay. Let's see here. Well, you know what? I might come back to that proof. That's going to take like another 10 or 15 minutes. So let's actually practice one of these using the mean value theorem. Okay, so it says in this example I have, it says find what? Leave room for the proof of the mean value theorem. Make sure that I get through this whole video before I run out of time. Okay, so we'll save space for that, and then we'll come up to here. It's a pretty long proof, so let's come up to here. Okay, so now we're going to say find the value C in the interval 1 to 4 that satisfies the MVT. And a lot of students get the mean value theorem confused with Rolle's theorem. They're not the same thing. Rolle's theorem is actually used in the proof of the mean value theorem. So I think that's why some people get it confused, but in general, or I shouldn't say in general, but they're not the exact same promise, okay? They have similar criteria, but Rolle's theorem has an extra value that it needs. However, the mean value theorem is a different promise. Promises that f prime of C, so Rolle's promises that f prime of C will be equal to 0 if you satisfy its 3 criteria. MVT promises that f prime of c will equal f of b minus f of a all over b minus a. Two different promises, okay? I guess you could say, well, if the slope of the secant line is 0, you could say that they're the same. But like I said, that's a specialized case. And that's all Rolle's theorem really is. But don't get the two confused. In general, it causes a little bit of problems for students. So let's please try to keep that off to the side over there. Okay, so let's use find the following C in 1,4 that satisfy the MVT, the mean value theorem, for f of x equals x cubed minus 8x minus 5. Or explain why it doesn't exist, why the C doesn't exist. Well, first of all, we know step 1, continuous since poly. Check. 2, differentiable. Why? Check. So we have our criteria satisfied. That means there is a C in this interval, okay? Where f of b minus f of a all over b minus a will equal f prime of c. So the first thing we have to find is the derivative. And this is going to be 3x squared minus 8. So we're going to change this to f prime of c is equal to 3c squared minus 8. And we know this has to equal f of 4 minus f of 1 all over 4 minus 1. So we have 3c squared minus 8 equals, and then we take 4 and we plug it in. Let's see here, should get 27, I believe, minus f of 1. Well, that should be negative 12, I believe, over 3. So we have 3c squared minus 8 is equal to, what is that, 13? Let's add 8 to both sides. So we now have 3c squared is equal to 21. Divide both sides by 3, and we should be good. So we have c squared is equal to 7. And then we're going to square root both sides to cancel. And we have c is equal to plus or minus root 7. Okay. However, what do you notice about square root or negative square root of 7? If we go back up here and look, this is from 1 to 4. So we're only taking positive c's. So we're going to throw out the negative, and we're going to say c equals root 7, square root of 7. That is our only actual c. Okay. So just keep in mind, all I did was I took and I plugged in 4 and 1. Plug 4 and 1 into, oops, that's pretty ugly. Do it like this. I took this guy and plugged them in, and this guy and plugged them in. Plug both of those into my function f of x and into this formula over here, right? And then where did the 3c squared minus 8 come from? Well, that's just me plugging c into my derivative. So we're kind of just plug and chugging, I guess. It's no big deal, all right? So this c satisfies the mean value theorem. So then at the square root of 7, this is a moment where the slope of the tangent line and the slope of the secant line are the same number, okay? So there's a little theorem that we can write that's a consequence of this, or that falls out because of the mean value theorem. If f prime of x equals 0, all x an element of the open interval AB, then f of x constant. Okay. So it says if f prime of x for all x in an open interval AB, if f prime of x equals 0 for all x in an open interval AB, then f of x is a constant. But that makes sense, right? Because if you're taking the derivative and you always get 0, well, that means the rate of change is always 0. That means that you had to have a constant value. You can't have a rate of change if it's always 0, okay? Let's look at another problem. Let's do some more practice. It says find all C that me see if I got a harder one. Let's see here. Let's try this one. I guess it's not really much harder. MVT equals x cubed minus x on 0 to 2. Okay, so take a minute, pause the video, make sure you know how to do this. Okay, so hopefully you guys pause it, you gave it your best shot. We have to do two things. First, we have to say, well, f of x is continuous since so since it's a polynomial. And then we also know that f of x is differentiable since it's a polynomial. Check and check. So now we can find f prime of x is equal to 3x squared minus 1. So then f prime of c is equal to 3c squared minus 1. And that has to equal f of 2 minus f of 0 all over 2 minus 0. Who says that has to be true? IMVT. The mean value theorem said this had to be true. Okay, that's its promise. Okay. So we have 3c squared minus 1 is equal to plug 2 into the original. We get 8 minus 2, which is 6, minus 0, all over 2. So we have 3c squared minus 1 is equal to 3. So we end up with 3c squared is equal to 4. Let's divide both sides by by 3. And I think we should be home free on this one. So we got c squared is equal to 4 over 3. So then c is equal to plus or minus the square root of 4/3. However, we know once again that we're on 0 to 2, so we're going to throw out the negative. And the square root of 4 over 3 is definitely in the interval. It's really c equals 2 over the square root of 3. That would be our final answer. And remember, you don't have to rationalize denominators in this class, but you do have to clean up radicals. So this would be the square root of 4, which is 2, over the square root of 3, which is square root of 3. Okay, so that's a little bit more practice with the mean value theorem. That's going to do it for this video. Please go over this and ask me in class about this video next time we meet. All right, everyone, I'm going to end it, and thank you.